Okay. So today we want to talk about cryptography. We last week we kind of talked about the basic things about security. What are the main principles? What should we care about, and so on and so forth. I also started discussing how we actually build a trust on a computer. We talked about a very important module called the trusted platform module. And we said that basically this is where we kind of trust, and everything else in the outside world of the computer is basically untrusted. So whatever we want to trust, we need to kind of like verify with the CPM. If we verify it, then we kind of like gradually increase this root of trust until at some point we kind of like trust almost everything about the computer. We're gonna actually talk about what would happen when we are dynamically change things. Unfortunately, it's not as simple as which we verify something statically and we can just move forward with it. Things gets much more messier and much more complicated when there's a dynamic interaction. And most part of this course will be about that. But of course, the first building block would be just trusting the system statically and start from some good known models that you can trust and then build on top of them. During that discussion, I talked about things like hash functions. I talked about keys and stuff like that. So it's better actually to talk about cryptography a little bit before actually jumping into all these procedures that we're going to use in this course. So this lecture and probably next lecture, we're going to focus on some basics about cryptography, which we're going to use later on in the course. So generally, I'm going to talk about fundamentals. A few things to mention is we are just going to go through intuitions and ideas. We're not going to have time to go over the proofs and mathematical theories behind it. It's very important, very useful, and very interesting, but unfortunately, we don't have time to go over it. The options is, once you get the basic idea and the intuition of what we are doing and why we are doing it, probably you can have some readings or taking other classes or watching some other lectures to get some ideas of the actual theoretical part of it. For those of you who are interested in a little bit of more theory, I highly recommend you to dig a little bit deeper on this and read a little bit more about it. But in this lecture and the next, we're going to mainly talk about the intuition and basics. So I'm not going to give you proof. So you have to just take my word for it. All right. Any other questions about anything else before we jump into the crypto part? Oh, at the end, I'm going to talk a little bit about paper readings and things like that as well. So, all right. Good. Okay, so obviously the first question is, why do we need cryptography primitives? I think most of you already know the answer for this, but the main basic questions for cryptography and the main reason that cryptography is so popular is because of the very critical use cases that it has. Main thing is communication among multiple parties. The idea is that we want to send something from point A to point B, and we only want to make sure that the transmitter and the receiver are the ones who see this message. And anybody in between, even though they can intercept the signal, they can literally see the zeros and ones, they cannot understand what this says. It's basically thinking about this, it's a different language that you don't know, right? So, and then the beauty of cryptography is actually there are mathematical truth and mathematical proof for why we cannot break the system. So it's not just, oh, it's something hard and we cannot break it. It's actually, there is hard theory behind it to prove that this is actually indeed unbreakable. So communication, of course, is one of the key aspects, but there are also other things that are important, and we're going to discuss this in this course as well, especially on the next lecture. Things like authentication. So, for example, how do we trust a user? And this is kind of like an identification or authentication problem. So If I say I'm person X, how can you actually verify that I'm indeed that person? Another thing is that we talked about integrity, right? So we said that, for example, one of the key things in security is making sure that if you send a message, the message that has been received is not exactly, it has not, is exactly what the transmitter was supposed to send, and it hasn't been modified. So how actually we can achieve that is through the cryptography. So there's this concept called message authentication codes, or MACs, which actually we're going to talk about again, hopefully in the next lecture. All right. So again, so to give you a little bit more background, confidentiality and privacy, going back to that, CIA things that we discussed so far. Encrypting messages can help us with confidentiality. For integrity, as I just described, making sure that the message is not being compromised. And for authentication and trust, we need to show that something is valid, or something is genuine or verified. So all these things are actually can be achieved through some sort of cryptography primitives that we're going to discuss. To give you some background, cryptography has been used extensively in the past. The very first thing, I mean, it actually goes back into like maybe 2,000 years ago with what's called a Caesar crypto system, which basically Caesars was something very basic that so the alphabet was shifted by some value. So for example, if the shift was equal to 1, basically A was mapped to B, B to C, and so on and so forth. And people have found that you can basically play with this number in order to create something that is very difficult for the others to understand easily. But of course, I mean, it wasn't a secure method because it can always brute force 26 different possibilities in order to actually find this, right? One of the more actual useful and military grade or consumer level grade crypto system was this Enigma machine that I'm showing here, which actually used by German during World War II. They used it extensively for encrypting their messages and communications among different units during the war. And probably most of you know the story of breaking this machine, Enigma machine, which originally done by some theorists in Poland and mainly done by UK, especially Alan Turing, which is kind of like very famous computer scientist. And of course, his colleagues that significantly believe that this is actually what caused the war to be much more shortened and significantly helped the Allies to kind of win the war. To just understand how an Enigma machine works, it's basically this simple machine that instead of like shifting things to left or right, it's kind of similar to the Caesar, but it's basically randomly map a character to another character. So for example, so usually the key is something that decides what is mapped to what. So for example, A can be mapped to K, B can be mapped to, I don't know, E, so on and so forth. So everything can be mapped to something random, and the mapping, of course, has to be one-to-one. Otherwise, you cannot recover the message. But it's just much more difficult for brute force because you have to kind of like map all the possible permutations, and for alphabets this is like a huge number, right? So it's not something that can go one by one. And this is kind of what's secure, but as we're going to go through the examples and design of a crypto system, we're going to see that this is not a secure way of encrypting things. We're going to discuss why, but at that time it was fairly secure. But as I said, actually it was broken by the Allies, and that was the reason that Germans wasn't that successful in the war. One of the main reasons. All right, any questions so far? And if you're interested about the Enigma machines, this is a very interesting website. If you click on it, you'll see that this is actually kind of like, if you guys have heard about Wordle, this is kind of similar to that in terms of you have to basically try to see if you can break the Enigma machine and guess a specific word. It's actually a sentence, not a word. But yeah, it's an interesting game if you're into it. All right. So now let's get actually to the part that we want to talk about why and how we need to build a crypto system. So generally, the things that we're going to discuss in crypto systems, it would be based on some fundamental assumptions, all right? Typically, what we do is making some basic assumptions about some NP problem, and then use some mathematical proof to show that this algorithm, this encryption or decryption algorithm, or this hash function, et cetera, reduce eventually to that hard problem. And since we don't know how to solve that hard problem, by convention, we can show that we cannot really solve the encryption problem as well. Kind of similar to the idea of like how we trust computers, right? We trust a piece of hardware that we think it's secure, which is the TPM, right? And then we kind of like build on top of it. For crypto, it's also kind of the same. So we start with kind of like trusting or assuming that some problem cannot be solved. And these usually are NP problems. For most of you have taken some algorithm course, you already know what those problems are and why we cannot solve them. And then there's usually some mathematical, derivation that shows that this actually leads to our crypto system, whether it would be an encryption or hash function, et cetera, et cetera. And then basically similar to things that probably most of you have taken an algorithm course to know, that there is a reduction, part which you show that if I can solve this, it means that I can solve this. And since I cannot solve this, it means that I cannot solve this either, right? So this is usually the trick during solving algorithms. So that's where, the hardness and the proof or guarantees about that this encryption system is secure usually coming from. All right? Any questions so far? Okay. So of course, before actually getting to the how we do this, it's important to know what are the challenges. The first challenge is that some of these assumptions may not be true and may be proven incorrect. Of course, it's the same story with the NP problems. Another part that we're gonna show to you is actually some of these is actually the hardness of these problems rely on the fact that what we assume about the power of brute force. But most of these, since there is no actual solution for example, breaking a crypto, the best known solution usually is the brute force solution, which means that the attacker has to basically check one by one all the possibilities. So think about for finding your keypad, your iPhone, for example, password. If for example, it's 6 digits, you basically start from 0000, 0001, and all the way to all the possible digits in that 6 digits possibility, right? And you can make an assumption that this brute force takes X amount of time, and basically your security of your password is basically that amount of time, right? So assuming that the attacker has physical access to your iPhone, they cannot find that password on average that amount of time, right? So when we are usually assuming about security of these crypto systems, we're also doing the same thing. We are assuming that each query takes X amount of time. This is the amount of query, so this is the amount of time that this system is secure. And usually these days is in order of hundreds of years. So for example, the RSA algorithm with current modern computers takes about more than 100 years to be brute force and attacks. And this is very, very, very secure. But as some of you have heard about, for example, quantum computers, quantum computers can actually break the RSA systems in order of minutes, 6 minutes, ideally. And the reason that quantum computers all of a sudden can break the system is not because something has changed. It's basically because quantum computers can do the brute force, that specific brute force that can be used for RSA much more faster. And that's the reason that RSA is no longer secure for quantum computers. So what I want to discuss basically, and wanted to point out is some of these assumptions as we progress and come up with new computing technologies, it might change. The third thing to remember is that the implementation, as I said before, can introduce bugs. So the algorithm is correct, the mathematical proofs is correct. What happens is when you're actually implementing as a piece of software, you might introduce some attacks. And finally, there will be a huge discussion on side channels and how side channels can break this. So I'm going to reserve this into later half of this course to talk about. All right. So now we know what are the challenges. Let's actually now talk about what is a crypto system, how it works, what are the mathematical definitions for it. So just a very high-level view of a crypto system is basically four things. Usually there is a secret value, which is, we call it a key. We're going to talk about two main crypto systems, the public key or asymmetric crypto systems and symmetric crypto systems. So in asymmetric, we're going to have a pair of keys, the public and the private key. And in symmetric system, we're going to have just one single key that is shared among the users. We're going to discuss why we need two or why we need one in each of them. But for now, assume that you might have one or multiple piece of information, which is usually something that is in order of 256, maybe sometimes 1024 bits, something in that order, which is the secret part. That's the only part that needs to be kept secret from anybody else. If this information is known, then the crypto system is no longer secret. The rest of these is actually what can be public. The crypto algorithm is actually the actual algorithm that's being used in order to do, for example, encryption, for doing the MAC or doing hash and so on and so forth, which we're going to mainly discuss in this lecture. And of course, there is the input and output. So we typically call the input message, and if you're using encryption, we call it plain text. And the outputs, depending again what algorithm are we using, is the output of the system, the encrypted message, for example, which we usually call it ciphertext. And if, for example, it's coming from a hash function, we call it hash and so on. All right. And as I discussed in the first week, everything about the algorithm should be known public and should be publicly available. So you cannot come up with an encryption mechanism and say that part of this algorithm is not known to anybody. If you actually search, you will see that you can actually see the exact step-by-step encryption of consumer grade encryption algorithms such as RSA and AES and so on and so forth. So you cannot assume that the algorithm itself is not known or secret. The only secret part is actually that value that we are storing, which we call it key. All right, so that value is secret. Rest of it is just basically a public knowledge. All right. So now let's talk about the two main cryptography methods, the symmetric key and asymmetric key, asymmetric cryptography models. The asymmetric sometimes also called public key encryption. All right, so we call it either asymmetric or public key, and symmetric is obviously the symmetric. In symmetric, the main difference between symmetric and asymmetric is, in symmetric, there is only one secret key, one value, that is somehow shared among trusted parties. So if, for example, three parties want to talk to each other, we need to find somehow a way of sharing this secret value among them. We're going to later discuss how we share that, but for now, let's just assume that we found some way of sharing this secret value among these parties. And for both encryption and decryption, for any of these parties, we're going to use the exact same key. So that one value will be shared among all of them. Any message that needs to be sent or received will be use that key in order for encryption and decryption. All right. The asymmetric one is actually a little bit different. The difference between asymmetric and symmetric is that asymmetric use a pair of keys, what's called a public key and private key. These are two different values. The public key is actually shared among everyone, so it's not secret. Everybody knows what is your public key, but the public key is actually something that is unique for each person. So if two parties or three parties wants to talk to each other, each of them has their own public key and each of them has their own secret key. So it's not the same thing that is shared among. right? And private key is basically what is kept secret and is unique for each person. So again, two parties wants to talk to each other. They share their the public key to each other, but they kept their secret key to themselves and they keep it secret, right? So now we're going to discuss these two in more details, and we're going to start with this symmetric key. Before that, just know this notion or this concept called primitives. Basically, primitives is kind of think about it as basic blocks in cryptography. So we want to achieve a specific task in security, and for that we use those primitives. The popular ones are encryption or decryption. Secure hash function is another one. Message authentication codes or MACs is another one. Digital signatures is another one, and so on. So these are different algorithms for different purposes. We're going to first talk about these, and then later on we're going to talk about these things as well if you have time. All right. There's also other protocols and primitives. So these are basically built on top of those primitives. So we have, for example, encryption and decryption or hash function, etc., etc. If we use this in some manner or shape, we come up with some protocol. These very famous protocols that probably you have heard about. TLS, which basically is the main method for communication on the internet, right? Which is basically based off asymmetric encryption, digital signatures, hash function, etc. So it's a combination of all those algorithms in some specific fashion. Login systems usually use cryptography primitives in different shapes and forms. Some of you probably have heard the term zero knowledge proof. That's also another protocol. The key exchange for exchanging the keys is another protocol. Multi-party computation, secret sharing is another protocol. Blockchains, which probably most of you have heard about, is another protocol. So these are different protocols that based off these primitives that we're going to discuss in this course. Of course, we don't have time to talk about any of these, unfortunately, but I mean, if you're interested, once you know those basic blocks, then you basically can just follow that, how these basic blocks are kind of connected to each other to achieve this protocols. Any questions so far? All right. So now let's focus on the encryption or decryption primitive. And I'm guessing that the majority of this lecture would be just talking about this, and even some part of the next lecture. And then if we have some time, we will talk about other things such as hash function and stuff. So encryption, decryption is basically two different algorithms. For encryption, we have an algorithm called E or encryption, which basically usually takes two inputs, the message and the key, and it outputs the encrypted message, which we usually call ciphertext. Decryption it's another algorithm, but we usually call it E, which also takes two inputs, the ciphertext and the key, and the output of it would be the actual message. All right, so this part is basically the receiver, and this part is the transmitter, the sender. For now, we are talking about symmetric systems, so that's why we use the same key for transmission and for reception. All right. So from now on, I'm going to just basically focus on the symmetric part, and later on, we're going to discuss what would happen if we have an asymmetric system. There are one main property for any encryption system, and that is what's called a correctness property. Basically, the correctness property says that if we encrypt a message and decrypt it, we obviously have to get the exact same message. So decryption of an encryption of a message should be the message itself. Otherwise, the message will be lost during this transmission, right? So you want to make sure that whatever you send the receiver, when they decrypt it, they're going to get the exact same message that you sent. All right. So for any encryption mechanism, whether it's symmetric or asymmetric, there should be this correctness issue. Otherwise, it doesn't make any sense. There's another optional property for encryption mechanisms, which later on we're going to actually discuss why this is important. And that's what's called a homomorphism. So what homomorphism says is that if you have two different messages, M1 and M2, and we apply some function to it, let's say, for example, a simple addition, so M1 plus M2. The homomorphism says that if the encryption system is homomorphic on that function, if we encrypt those messages and apply that function and then decrypt the message, the results would be as if we are added them on the plain text domain. So for example, if you have 2 and 3, I encrypt this and say it's C prime, or let's call it C1. And I encrypt this and call it C2. Oops. And now if I, instead of adding these together, I just add these ciphertexts together, and let's call it C3. And now if I decrypt this C3, the results I'm gonna get, which I'm gonna call M, would be equal to 2 plus 3. So it would be 5. So in other words, what homomorphism gives us is the ability to do some function evaluation on the ciphertext domain. And this is not something that applies to every encryption mechanism that we have. Some encryption mechanisms do actually support the homomorphism and some don't. And the function itself also matters. So for example, some encryption mechanism can support addition, but not multiplication. It could be the other way around. It could be both. It could be neither, and so on. So this is not important for now, but later on in the course, you will see why homomorphism is important for us in some other applications. So just keep this in mind. For now, let's just focus on the correctness attribute, which we want to make sure that whatever we do during the encryption or decryption process, the message can be recovered no matter what. Okay, so now let's start with, if we want to do an encryption, what is a secure algorithm? So what is a secure encryption mechanism? What do you want to achieve? Any thoughts?
You want to make sure that you can look at the encrypted message, sorry, the ciphertext, and then figure out what the encrypted message.
Okay, cool. Any other things to add to it? So this is fairly accurate, but there are some small things that we need to pay attention. So generally, exactly what you said, that it should be hard to completely determine M from C from the ciphertext without the knowledge of K. Of course, we want to make it very, very easy to determine M from C with the knowledge of K. That's actually basically our decryption mechanism. So we want to be able to easily decrypt it with the knowledge of K, but very, very difficult without having to. All right, so that's basically what we want to achieve on an encryption algorithm. But there are some faults as well here, right? So when we are saying not being able to determine M from C, one obvious question would be, what about partial information? So let's, for example, say that M is 64-bit and C is also 64-bit. And for some reason, I can, for example, tell by just looking at this ciphertext, I can tell whether the message was even or odd. Okay, so just looking at the pattern of ciphertext, for some reason, I can tell that whether the original message was even or odd. Do you think this is considered as a secure message or secure encryption system or not? I can only tell this is even or odd, nothing else about the message. Do you think this is considered as secure or not? How many people think this is secure? 2, 3, 4. Okay, and the rest, I'm assuming, thinks that this is not secure. Okay. So the answer to that, it depends. Most of the times, as we're going to discuss, this is not a secure message, encryption systems. But in some specific scenarios, maybe it is. So we're going to actually talk a lot about this in the next few lectures. And another thing to also consider is the attacker's capability. So basically what the attacker can do and how the attacker can interact with our crypto system. Generally, 3 things to think about for now. We're going to actually add another 4th point here later on. But 3 things that the attacker can have achieved, and this is kind of in this order, is actually increasing the attacker's capability and strength, is the attacker can only maybe see the ciphertext. So basically, the attacker might see a final list of ciphertext, and by that, maybe can predict what the M is for each of these. So that's one capability that obviously the attacker can have. The attacker might be actually a little bit more more powerful and have some knowledge about the plain text as well. What does that mean? It means that basically the attacker has access to some pairs of plain text and ciphertext. And again, this is a finite list of pairs. So for example, we can play with this algorithm to actually get something encrypted and see the ciphertext of that as well. Of course, when we want to say M, we are talking about an unknown M. So let's say we have, for example, K of these, pairs, and we want to see whether we can basically detect the K+1 message, right? So we have list of K pairs of ciphertext and messages, and the attacker maybe can build a model and do something about it. And finally, we want to see whether the attacker is capable of saying what is the M K+1 message is or not, right? So that could be another capability that the attacker has, and we usually call it a known plain text capability or crypto system. And finally, the attacker can have a little bit more power than just knowing the pairs, but knowing what's called a chosen plain text, which means that the attacker can basically choose what sort of pairs he or she can see. So for example, the attacker can say, I want this message, and this message, and then I can basically query the model to get C1, C2, C3 of these. So it's not just a random list of K different pairs. The attacker can actively choose a specific message, for example, yes or no, or specific number, or specific string, and so on and so forth, and then query the model to receive those ciphertexts. So that's also another option that the attacker can have, right? And we typically mainly focus and assume that the attacker has this ability of choosing the ciphertext. We call it chosen plain text attacks, CPA. And we usually want our crypto system to be secure against CPA. So when we, for example, say that this crypto system is CPA secure, it means that even if the attacker has access to, these pairs of chosen plain text and their corresponding ciphertext, if this is a finite list of pairs, the attacker cannot, again, predict what is the next message is when he or she sees these ciphertext.
So what exactly is the difference between this and the known plain text?
The known plain text is the attacker has not the ability to choose what that known plain text is. So let's say, for example, I'm the designer of this the crypto system. I'm going to give you a list of some plain text and some ciphertext. You don't have the option of choosing what sort of plain text you want to get. With the chosen one, it basically can tell me, here are the words that I want you to encrypt for me and give me the encryption of it. So I'm going to pick those words, encrypt it, and send it back. Any other question? So we want our systems to be CPA secure, and then we're going to discuss why and how, all right? So now the question is this accurate enough? That's having no knowledge of not being to, partially or fully, recover a message from a ciphertext. Is this enough for them? And to understand that, let's just give an example of two messages. So let's say that, C. Of course, by seeing C, the attacker cannot tell whether this is M or M1 or M2 with 100% accuracy. But with some accuracy more than 50%, the attacker can tell this could be M1 or M2. So basically what we're saying is that the attacker cannot, by seeing C, cannot say this is 100% M1 or this is 100% M2. But maybe with 70% can say this is M1, and with 30% can say this is M2. And remember, the random should be 50%. So by just flipping a coin, the attacker would say this is 50% and this is, I mean, there's a 50% chance that this is M1 or M2. All right. So based on this assumption, may not be completely accurate because we might consider this as not a secure mechanism as well. All right. So what is a perfect mechanism and perfect secure encryption system? So there's actually a mathematical definition for what's called a perfect secrecy. And the perfect secrecy is basically saying that for every two messages in our message domain, so think about the M as a set of all possible messages, and pick any two of those messages at random. And for all the ciphertext in the ciphertext domain, which basically is the encryption of these two messages, and for any random K that is uniformly distributed over the set of possible keys. So let's say, for example, the possible keys are 64-bit values. So any of those is uniformly distributed among this key set. The perfect secrecy says that this encryption system is perfectly secret if the probability of seeing C coming from M0 is exactly similar to seeing C and it's coming from M1. Basically, just intuitively, what this says is that if I see any ciphertext, I should not be able to tell which message is this with more than 50% chance. All right. If I, for some reason, I can tell with more than 50% chance that this is probably this message or that message, this encryption system is not perfectly secure. Does it make sense? Any questions? Yeah.
Where's the 50%?
So 50% for this specific case is because we have two messages. If we have n messages, that should be 1 over n. So 1 over 2 for two messages, 1 over n for n messages.
This probability is without any prior knowledge.
What do you mean by prior knowledge?
Like it's just
So we are assuming that we are CPA secure. So the assumption is that the attacker already seen a set of finite messages and ciphertext. And even if it has seen those, it should be for a new ciphertext that the probability should be. Does it make sense?
Yeah, does like two different messages have the same encryption?
Yeah, the encryption algorithm and the key is exactly the same. And then we produce two different ciphertexts. The attacker should not be able to tell which ciphertext is coming from which message.
And if we encrypt the same message twice, do we get the same ciphertext?
We get the same ciphertext. We're actually going to talk about that part as well. That if we do the same thing over and over, what will happen. But for now, it's a deterministic algorithm. So if you give same M1 and same K, you will get the exact same thing.
On this slide, I'm kind of confused on what M1 and M2 are. Are those the set? Are those elements of the set of all possible messages?
Yes.
Okay.
So I mean, according to this, it said for all. So all possible messages in the message set. So to make things simple, think about message set as 64-bit values. So basically, any number that is 64-bit long, which we're going to be 2 to the power of 64. Any of those numbers, if we randomly pick two of those numbers and encrypt them using the key, the probability that we see the ciphertext and say which one is the one that has been encrypted should be exactly the same. All right.
So basically, like the probability of C coming from M0 is the same as C coming from.
Yes, yeah, that's exactly what this is, right?
Is the plain text the same as the messages?
The plain text and message is the same, yes. So again, the encrypted message C is called ciphertext. The message is called plain text.
M1 and M0 and M1 aren't equal, right?
No, they're two randomly chosen messages.
So how two different messages are being encoded to the same
They're not getting encoded. So we are saying that if we see C, the chances that the original message was M0 or the chance that the original message was M1 should be exactly the same.
Okay, like it's very hard to attack.
Yeah, so we are saying that if we see C, we should not be able to tell that this was coming from M1 or was it coming from M2 or M0 or M1. It should be equal chance for them.
Can you express this conditional probability?
We can probably express it as conditional probability. Yes. Any other questions? This doesn't follow. Okay. So this is what we call perfect secrecy, and we want to achieve this. And of course, the million-dollar question is: can we achieve perfect secrecy? Is there exists an encryption mechanism that we can achieve that? And the good answer is yes. And that's what's called a very simple thing called one-time path or OTP. The OTP is like this very, very simple encryption mechanism that all it does is basically just XOR the key with the message. Oops. So it's the encryption system is basically just a simple XOR. And is there anyone who doesn't know what XOR is? Everybody knows. So this is just the XOR of M and K, and the ciphertext would be C. There is one key part, and that says that the size of the K, the length of the K should be equal to the length of the message. And if that's the case, then this encryption mechanism, which is called one-time path, which basically just padding the message with some key, can achieve perfect secrecy. All right. There's mathematical proof for it that why this is satisfying that requirement that I showed in the previous slide. But again, we're not going to go through the proof. All right. So basically, the encryption would be very simple. I'm getting a message. I'm having the key. I'm just going to go and say that MC is the XOR of M1 and K. And we already know how the XOR gate works. So it's very simple in terms of implementing this. And the decryption, interestingly, is also the exact same thing. So basically, for recovering the message, all I need to do is XORing the ciphertext with the key. And probably if you know some basic logic, you will see that XORing of the same thing over and over, basically this would result in 0, and XORing something with 0 will be just itself. So that's why this is actually a correct statement. All right. So basically, all we need to do is for encryption, we take the key, we XOR it with the message, we get the ciphertext. For decryption, we also do the exact same thing. We take the ciphertext, XOR it with the key, and we get M back. And the reason is that if you XOR something twice, you get your results back. So basically, you're just nullifying the effect of the key on the message. Other question? You have a question?
It's like with the key that simple, it just does an XOR.
Yes, it's just simple as that. You just do XOR, and you cannot recover it. There's proof for that. You cannot recover it if you don't have it. Okay. So simple as that. That would be encryption and decryption. But of course, this is not. I mean, if it was this simple, probably this would have been done, 50 years ago, and there wouldn't be much research on cryptography. So the biggest catch in this is that the key size and the message size should be exactly the same. All right. And why this is an issue, just think about your, for example, hard drive, which has a 1 terabyte of data, and you want to encrypt this 1 terabyte of data. What should be the size of your key? Your size of your key should be also a terabyte. And where you're going to store that key, you're going to store it probably on the same hard drive. So basically, for any M bytes that you want to encrypt, you need another M byte for your key, and that is not feasible at all. So we are basically saying that you can only use 50% of a storage for storing regular things. The rest of the other half should be used for storing the key. And that's not just one problem. It's actually, think about the way that we want to communicate with other people. For every message that we want to send, we need to somehow find a way for sending the key as well with it. And that's kind of defeat the purpose, right? So if we already have a very efficient way of transferring the key, we might as well use that for sending our messages as well, right? So this is not a way of communicating things easy. So for example, for SSH, you're not sending 1 terabytes of data to start the communication. You just send very simple and small things that we're going to discuss, and then you can encrypt millions and millions bits of data just based off that very tiny key that you have to send, right? So that's the biggest problem with the one-time pad, unfortunately. Although it gives us what we really want, and the encryption and decryption is actually quite efficient, it unfortunately is not satisfying the requirements that we have in modern systems, which we want to be able to quickly send and receive things in large sizes. All right, any questions here? All right, so before I actually say, okay, what should we do? 2 more things that we need to think about, and you already asked this question. So, so what would happen if we, encrypt the same things twice, right? So since this is basically a deterministic algorithm, if for example, let's say we want 2 messages, yes and no, and when I'm encrypting yes with the key, so this can be represented with some numbers, right? So at the end of the day, I'm just XORing some bits with some bits and get C1. And then if I do the same for, let's say, the word no, I get the second ciphertext C2, right? And if I keep encrypting yes over and over again, I'm going to get the same C1 over and over and over again, right? And as I already told you that this is perfectly secret, there's no problem with it. But now think about from the attacker perspective, the attacker does not know which one is which. So by seeing C1, the attacker cannot tell whether this is yes or no. But since if we keep repeating this, the attacker can tell the frequency of these 2. So basically can see that, for example, C1 happens 10 times maybe, and C2 maybe happens only 1 time. And maybe by knowing the context, the attacker can know which one is which. So for example, for some reason, the attacker knows that this is a questionnaire, and most of the answers should be probably yes. So as a result, by just saying that, the frequency of C1 versus frequency of the C2, although the attacker mathematically cannot tell C1 is M1 or M2, by just looking at the sheer frequency of these, the attacker can tell that, oh, this should be yes, and this should be no. All right. So lots of questions. So one thing before answering the questions is basically what this tells us is that, of course, we get perfect secrecy, but repeating, or what is called many-time pad, may not be as secure as one-time pad. So what we are guaranteeing here is one-time pad is perfectly secure, but many-time pad, which is repeating over and over again, is not necessarily secure. So questions?
Are you talking about like on a bigger scale? Because like how can you exclude these?
So for example, in this case, let's say each character is 8 bits. So for example, in this case, we will have, let's say our messages are 24 bits. So our key should be 24 bits. And for no, what we can do is just pad it with 1. So we say that our message domain, which is M, is, for example, 24 bits.
You could still do like yes and then
You can pad it, right? So it depends on what is your message size, really. Or another thing that you can do is, for example, let's say if you want to encrypt this sentence here, and I'm telling you that you can only do 3 characters, they can break this down into 3 characters and do three character, right? We will actually talk about that as well. Other questions?
do you assume that the attacker may possibly know
The attacker possibly know what?
the key? Okay,
No, the attacker does not know it.
okay, all right.
So I mean, the whole in every single crypto system that we're gonna talk about in this course, we always assume that the attacker does not know what the key is.
Okay, because otherwise this thing like you just XOR K again and get the original.
Yeah, of course. If you know the key, you break the crypto system anyway.
So this drawback is what happens if we only have one key and we reuse it, right?
Yes, if you have a deterministic algorithm that it basically we're only talking about one-time path for now. So just focus on one-time path. So what we are saying is that one-time path is secure, perfectly secret. But many-time path, which means that if I keep repeatedly use one-time path for the same message, that may not be secure because the attacker might have some extra context about this and use that to just do some what's called a frequency analysis.
Okay, so this slide is for
For one-time path only.
one-time path.
Yes. Any other questions? Something on the back? Good. Okay. So what should we do now? So as I said, this is basically the comparison, which is what's called a deterministic. And I'm also putting the word probabilistic here. With the later on, I'm going to talk about what this is and how we can actually basically solve this problem with that. So I'm going to give you some hints. So two main issue with one-time path, right? The first issue is that the key size has to be the same size as the message. And I gave you some examples of why this is not feasible. And the second problem is that one-time path is only useful for encrypting a message once. You cannot use it for more than once, 2 times, or many times, right? So these are the two key issues. And both of them are the things that we absolutely need, right? So we cannot have a large key, and we really need to be able to encrypt the same message over and over again in our communications, all right? So we need to find a strategy or solution to fix these two problems and coming up with something that fixes these two. No, the padding was for fixing this issue of the message size. What I'm saying is the issue is that if you have a message that is, for example, 1 terabyte or 1 gigabyte long, you need a key that is also 1 gigabyte or 1 terabyte long. What's that? You cannot pad a key, yeah. So the whole, sorry. You cannot. So the whole mathematical proof of one-time pad is that one-time pad is only perfectly secret if the size of the message and the size of the key is the same. If the size of the key is much smaller than the size of the message, there's a mathematical proof that this would not be perfectly secret. Again, we won't have the proof, but just take my word for it that the only requirements for one-time pad to be perfectly secure is that the size of the key and the size of the message should be exactly, not even 1 bit less. Okay?
Just put the message into size K. Let's put the message into size K.
You can do the messages in multiple, yes, you can. But so for example, your 1 terabytes could be into smaller pieces of whatever you basically what you want to have. But then you run into the second issue that you cannot do many times, right? So at the end of the day, the chances that you get, messages that are very similar to each other is very high. So yes, either you can say my message size is really big and then I need a really big key size. Or you can say, yes, my message size is very small and as a result, I'm going to use a very small key, but then you have the issue of many times. Any other questions? So what should we do? So let's focus on the same first problem first. first. Let's see what we can do to fix the issue of the key size. So one interesting, development was that we basically may not necessarily need perfect secrecy, because perfect secrecy is this very ideal scenario that this guy is very persistent. Let me see if we can. Sorry. So perfect secrecy is this algorithm that is kind of like perfect and is only saying that you have absolute zero chance of detecting what is what. What people have found is that actually what we can do is what's called semantic security, which in some sense is weaker version of perfect secrecy. And what it says is that, remember we said that this probability should be equal to each other. So basically this number should be equal to 0. The semantic security is saying that this number should be negligible, all right? So basically if I see C, the chances that I'm telling whether this is M0 or M1 should be 50% plus some very, very tiny number, the epsilon. And with that, I'm gonna get semantic security. So of course, the first question is what is negligible, right? And this is the assumptions that we're gonna make in our computer systems. And remember, I said that some assumptions might change over time and may not be correct. For now, at least, thankfully, semantic security or the assumptions that we have for semantic security has not been broken. So we typically, when we are saying negligible, we are talking about order of 264, or if you want to be more secure, we're talking about 128. So when we're saying negligible, we're talking about 1/164 or 1/128. All right. So when we're saying this is that with this probability plus the 50%, the attacker might be able to say that this might be this message or this message. But this number is so tiny that for practical purposes, the attacker cannot really break the system, right? So that's the difference between semantic security and perfect secrecy. And you might ask, okay, how does this help? The help that we get from the semantic security is that, very interestingly, again, there's a very interesting mathematical proof for that. But by saying that basically we can tolerate this amount of epsilon, there is a mathematical proof that says that with this, we can actually now use one-time path with a key that is much, much smaller than message. All right, so it's kind of like we can basically use the key for different parts of the message, as long as we are kind of be able to tolerate this amount of epsilon. What is the relationship between this size and this epsilon? There is a mathematical derivation for that as well, which we're not gonna cover in this course. But again, there is theoretical work that shows that how by tolerating this amount of tiny difference, we can have a much, much smaller key compared to the message.
But how would we say we do an XOR if it's like much smaller?
So you break down the message into smaller pieces and then do the XOR, right? Any other questions? So this semantic security is one of the interesting development that happens about 30 years ago. It's kind of like changed the whole landscape of crypto systems. So to give you a little bit more insight and intuition about what is semantic security, there are some richer guarantees that come from the semantic security to maybe help you a little bit with to understand what is semantic security, or what semantic security is basically guarantees. One of them is what's called a message recovery attack. So what is message recovery attack is basically saying that if I have a set of possible messages M, and if I pick one message M prime and send this to the attacker, encrypt this message and send the encrypted version to the attacker, the chances that the attacker can recover this message, can tell what this message is, the probability of that should be 1 over m plus some epsilon, right? So again, if the message size is big, the attacker cannot really tell what this message is with a chance of 1 over m plus some epsilon. And you already know that if this message size is big enough, for example, if we're talking about like 128-bit messages, we're talking about this number. And I already told you that this epsilon is also somewhere in that order. So we are talking about something in the order of 2 to the power of 127, something like that, right? This is the probability of recovering this message from the attack. And then if you calculate this, this is really, really, really small, right? So for perfect secrecy, we were saying that this number should be 0. For semantic security, we say that we can tolerate this number as long as our message space is big enough, and as long as epsilon is small enough.
So is M prime the encrypted message and M is the original?
Yes.
The 1 over 1, that's it.
Yes, one of them is the epsilon, the other one is m. So m is 2 to the power of 120.
And what is it's like your domain of
Your domain of messages. So for example, let's say our messages should be 128-bit long.
Okay, so it's like the domain of
All possible messages.
Okay.
For one-time path. So we're basically saying that, one-time path.
One time as you take the unencrypted messages XOR.
With the key, yes.
We attack the key instead, the key is smaller, with that noise is.
Yes, the key space should be also large enough. So again, you should not be able to do brute force for the key. So key space should be also large enough. So it eliminates the chance of any brute force. Correct. I might have actually needed to add this here as well.
We distinguish between an attack on the key and an attack on the crypto system, right? Because the user can choose a key, and so if the user chooses a key that's sufficient and long enough, then we don't really care about an attack on the key, right? So we would only be the crypto system.
So there is no distinction between attacking to key and the crypto system. Crypto system is just this black box that you're trying to attack. What you're trying to do is recovering the message that we discussed at the beginning, right? So for that, you either need some sort of context in terms of, for example, as I said, frequency analysis or something like that. Or the best thing you can do usually is just a brute force. You can either brute force on the key to get the message, or you can brute force on the message to get the key. One of these two. Does that make sense?
So instead of crypto system, when we rephrase to say, I guess the encryption algorithm, right?
Mm-hmm.
So what we're discussing right now is attacks against the algorithm, because the key can be chosen by the user, and so presumably they can choose a key that's long enough that would make a brute force attack possible.
Yes. Good. Any questions? So basically what the semantic security guarantee, one of the things that semantic security guarantee is this term here. But semantic security actually guarantees more than this, which again, we're not going to talk about, but to just give you some intuition, by saying that we are achieving semantic security, we are kind of achieving this, right? And then another interesting thing about semantic security is that it says not only the entire message cannot be detected, but it also says this is the same scenario for every individual bits in that message. So the chances that you can recover the first bit, the second bit, the third bit, and so on, all of them should be 1 over m, basically, okay? So it's not like, there is a bias between one bit to another bit. So I cannot tell the difference that whether this value is odd, this message has been odd or even. I cannot tell that whether the most significant bit was 1 or 0. Basically, the chance of detecting any of those bits is equally distributed among the length of the message, and all of them have the same property as the other ones. All right. So semantic security also guarantees this, which is very important for us in many, many scenarios. All right. So let's now see how we can build a semantically secure one-time pad. Before that, let's have a quick break of maybe 5 minutes and then discuss this. Okay. So now we kind of know what's going on. We want to see, okay, how do we build one-time, semantically secure one-time path? People ask, okay, what happens if the key is smaller? How do we do the XOR and stuff like that? So now let's actually talk about how do we do that. So the way for fixing the issue of the size of the key is it's fixed with what is called stream cipher, right? So the idea of this stream cipher is we start with some small c, and then we're kind of using a specific algorithm that's not a regular algorithm. It's something that is designed with this in mind in order to stretch this and then use it for the message. So for example, let's say our key is only 8 bits and our message space is 32 bits. If you want to do the XOR, we need a key that is 32 bits. In order to achieve that size for the key, we use this thing called stream cipher, which basically an algorithm that takes this seed, which is the original key, or we call it seed, and stretch it into a bigger size, which, for example, in this example that I'm giving you, takes an 8 bits and giving you a 32 bits. And that would be your basically your one-time pad key or old key or whatever you want to call it. Now you can take this old key and then just XOR it with your message to get the ciphers. And the same algorithm can be used on the encryption side and on the decryption side. So basically, both the sender and receiver agrees on the same stream cipher algorithm. They start with the same seed, so they get the same key, and then they can basically just use one time. And I already showed you that this can give us semantic security if the stream cipher itself is designed such that the stretching doesn't introduce additional challenges.
And is the reversal algorithm also true?
The stream cipher does not compress anything. It's just the stretch things. It cannot compress.
So you just use the stretch.
Yeah, it's not a reversible, or it might be reversible if people don't use it, but it's just a one-day function. But basically, the reverse of that is usually what's called a hash and a secure hash, which we're going to talk about. So you have a larger message domain, and for some reason you want to compress it. And that would be a hash, basically the definition of a hash function, which we're going to talk about. Are we good? So to give you a little bit more, mathematically, basically, we have our secret, which this time I'm showing it with term S. So basically, this is our key, but this is seed, so I'm showing it with S. It has the size of L, lowercase l. And then we have the message and ciphertext in the message size of L. And as I said before, the size of the key is much smaller than the size of the message domain and ciphertext domain. So in that case, our encryption mechanism takes the seed and the message and has two steps basically. First goes into this generator algorithm, this stream cipher, to stretch the S, and then it's going to XOR it with the M. So the output of the GS, basically GS is this function from L to L, right? So the domain is L, the output is uppercase, right? And then it's going to XOR it to M, and this way you're going to get your ciphertext. Decryption also gets the seed and the ciphertext. Use the exact same algorithm, takes the seed, stretch it, XOR it with C, and you get your M. All right? So that's the idea of a stream cipher and getting a semantically secure OTP.
I'm curious, is that G the same as like what you call generator from a communication system here?
What type of communication system?
Like now there's a pairing code. So something similar is also generated.
No, stream cipher is a specialized algorithm designed for cryptography.
Oh.
So it's not any sort of generator that stretches things. So you cannot just design an ad hoc algorithm that with one way or another stretch things. This is not the secure way of doing it. All right, so what is the requirements for this GS? Basically, the requirements is that the attacker should not be able to detect the difference between GS and the random string R, which has the size of L. Basically, what we're saying is that GS takes the size lowercase l and stretch it and gives you, let's call it K. The attacker should not be able to detect the difference between K and any sort of random string of the size uppercase L. When we are saying random, there is a specific statistical test for it. So basically, we are saying that the attacker sees lots of R's, R1, R2, R3, R4 from a random distribution. So you basically sample that random distribution. And also the attacker sees lots of K1, K2, K3, and K4. And if it actually fits a distribution for this and fits a distribution for this and runs a statistical test on it, it should not be able to see any difference between these, right? So some of you have taken probability courses, know probably what is a statistical test and what is probability and what is random. But if you don't, just think about that we see a series of numbers here and a series of numbers that's generated from a true random sequence. With some probability, the attacker should not be able to tell the difference between these. So in other words, the GS, the output of GS should look random, right? If you need more concrete mathematical definitions, you should know what is a statistical test and what is distribution, which we're not going to go through, unfortunately. Is that accurate enough? Is that clear enough? Cool. And we usually call this GS a pseudo-random generator. It's not a random generator, it's something that looks like random, so it's a pseudo-random. So we're gonna call it PRG, all right? And not every single algorithm is a pseudo-random number generator. It's not a cryptography secure or semantically secure PRG. There's specific type, there are specific algorithms that's designed specifically to have this semantically secure PRG.
Is that golden equals represent?
So it's here.
Yes.
So I mean, this is a terminology to show that this is a deterministic algorithm. If it's not deterministic, we're going to use another. We're going to use this basically. Any other questions? All right. So we kind of fixed this first issue, right? Combination of semantic security with stream ciphers gives us kind of fix this issue of the key size and the message size. So we can actually start with a very small seed that is much, much smaller than the message size. We feed this into some PRG, we get our key, and now the size of the key is actually same as the size of the message, and then we can do our old OTP here. and get the message and be happy, right?
Just to clarify, is G of S the extended C?
G of S extend S to key to K. Yeah. Does that make sense? But we don't, C is still generated by X ORing K by M. In order to get K, you start with S, you stretch S, you get K, and then you do your X.
And G is that function that stretches.
Yes. It's what's called a stream cipher, or in general term, it's called pseudo-random number generator, PRG. Okay? And I cannot stress this enough that not every single stretching algorithm is a secure PRG. PRG has to be designed with specific things in mind. We're not going to give you an example in this course, but again, if you're interested, just search for it. Okay, so now we fixed this issue. Now let's focus on the second issue, which is money time. So we have the capability of starting with very small key. And actually, I mean, these days, you know, this pseudo-random number generator is very, very efficient. So you can actually start with very, very tiny seed and stretch it really big. So you don't need to store for 1 terabytes of data. You may be good with even, you know, one kilobytes of data or something like that for the numbers. Is really depends on the algorithm, but basically the message here is the key thing here is that you don't really need a big size key. Okay, so let's see what should we do with the second issue. So one easy solution is, of course, how about doing a different key with different messages, or for the same messages. So if I want to have different, so if you have yes and no, the first time I'm going to use K1, and I'm going to encrypt this and get C1 and C2, right? Now, if I use a different key, K2, and encrypt the same two messages here, I'm going to get C prime 1 and C prime 2, and these two are not going to be the same values because the key is different, right? And if I want to do it multiple times, I use multiple different keys and be done with, right? So that could be one easy solution for this.
How do you
Again, we need to kind of agreeing on series of keys instead of agreeing on one, right? So basically what we need to do, which I was going to say, was instead of like agreeing in one key between the sender and the receiver, we need to agree on set of keys, key 1, key 2, whatever, right? But as I'm saying and showing here, this is not a feasible solution because, first of all, we don't know necessarily beforehand how many times we're going to encrypt the same message over and over again, right? And the second problem is that, again, we go back to the problem with key management, which it's very difficult to, you know, agreeing on key. So, you know, sharing the key is a very expensive protocol. And it's not something that we want to do very often. We want to do maybe only once and kind of be done with it. And so we don't really want to have a set of large keys and then, you know, continuously, you know, exchange this to the other receiver. So it's really what we want to do ideally is just, you know, agreeing on one key or maybe very finite set of keys and then have our encryption mechanism. So this is not feasible. So what is the solution for this? The solution, as I kind of said before, is that we cannot really use a deterministic algorithm for our encryption. Because the deterministic algorithm, if the inputs of a deterministic algorithm E is the same, it's going to always create the same output no matter what, right? What we really need to is a probabilistic algorithm, which basically, if I'm sending the same inputs, every time I'm sending the same inputs, it generates a different output. So in this case, I can use the same key, but if I send the basically same message M and K, it will generate a C1, C2, C3. So it's kind of like a distribution. So I sample it each time, and each time it generates a different output for me. And this way, we basically can use the exact same key, but each time get a different ciphertext. The big question though is if this is kind of probabilistic, then how do we decrypt? Because the decryption algorithm also needs to know what is the outcome, right? Because remember, we need the correctness issue and we need to satisfy that correctness requirement. And we're gonna now talk about how do we achieve this probabilistic behavior to satisfy the requirements of many time path without actually sacrificing the correctness issue. Any questions? All right, so the idea is actually quite neat and very simple. We can use the same stream cipher, and which basically I'm showing here graphically that it has the original seed, or let's call it the original key. The stream cipher takes this, and for now, just imagine that this doesn't exist. This would be our key stream or key. And this would be our basically our XOR, and this is our plain text data or a message, and this would be our ciphertext, right? And this part is basically our OTP. What the probabilistic one does is basically adding this additional random value, which we usually call it nonce. Nonce is, you can think about it as just a random value that each time that we encrypt something, we just randomly pick it from the from some random distribution. And the stream cipher, instead of just getting S, it gets the S and the nonce, and then create the key for us. And the way that we're going to design this G is if I change this nonce, even if I use the same S, the key would be different each time I'm changing the nonce. And this way, the key would be a different key, the message would be the same, and the ciphertext as a result would be different. Okay? So to just give you an example, I have message 1, a C, and nonce 1, I'm calling it N1. What I'm going to do is that I'm going to first send GS and N1 to it. I'm going to get K1. I'm going to XOR K1 and then 1. And I'm going to get C1. The second time I want to encrypt the same message, what I'm going to do is that this time I'm going to send M1S, but this time I'm going to send N2. And what I'm going to get is GS and N2. And the stream cipher is designed such that it generates a different key 2 for me. And then I'm going to key 2 M1, and then I'm going to get C2. So exact same message, exact same seed, different nonce, and as a result, different results. All right. And how do we decrypt, before answering your question, is all I need to do is that when I'm sending this message to the other side, I will also send the nonce each time. So basically, instead of sending only the ciphertext, I send the ciphertext with the nonce. And nonce doesn't need to be secret. It's just a random value. And the idea is that the decryption has the access to the seed. So this S is the same from the receiver side and from the transmitter side. It gets the nonce from that. It can generate the exact same key, and then it can decrypt it using one thing. All right. So questions?
The question about the nonce, you say it's random. Is it like a random Gaussian or is it any distribution?
No, it's a random guess.
So 0 means standard deviation 1 Gaussian.
Yes.
Okay.
Any other questions? So the trick that we really use is that extending this GS to a GS and some nonce, some value that is just randomly chosen. And the very important thing here is that in order for your many time path to be secure, you can only use your nonce once, right? So that's why it's actually called nonce. So you only need to use each value only one. So basically, the amount of time that you can repeat the same message is the size of your nonce. So if I want to repeat the yes message, encrypt the yes message over and over again, I can only, for example, start from 0 all the way to the size of the nonce. And of course, the nonce can be big enough, for example, 128 bits, 256 bits, and so on and so forth, that generally, in any feasible world, this is large enough that we don't really never actually, reach to the end of our nonce. Is that clear? Does it make sense? Cool. So yes, so I'm just here showing that this is basically where we are adding the randomness, and all of a sudden kind of changing the behavior of something that is usually deterministic to something that is fairly probabilistic, right? So all good, right? So we fixed this issue with basically a combination of stream ciphers and semantic security, and we are fixing this issue with extending our stream ciphers with accepting them. So the question is this satisfactory? Are we happy or not? And of course, we always greedy and we want more, right? So there are some issues with stream ciphers that we need to, do even more. And surprisingly, stream cipher is not the most popular method for encryption. And the reason for this is that this whole process of expanding the key and adding randomness and creating the key is not efficient in terms of time, in terms of latency. Just remember that we want to keep, encrypting and decrypting messages and do process with it. So our encryption and decryption is usually needs to be very, very fast in order for us to, for example, send and receive things over internet, receiving things from another user, and so on and so forth. So speed for encryption is extremely important, on top of course, the security. And that's why stream cipher is not that much popular. There are stream ciphers that are being used, they're efficient. If you're interested, search for one called Cha-Cha or Salsa. There is another one that used in the past called RC4, which no longer is being used because the people have found ways to break this. But there are fairly efficient stream ciphers, especially for low-end devices such as IoT devices and so on. But in more advanced systems, more modern systems such as your laptop or generally the internet, stream cipher cryptography is not what is being used generally. It's the other approach which we're going to talk in the next slide that's being more popular. But just to give you some perspective, how we create this GS plus nonce and so on. As I said, these are special algorithms. If you're interested to know how this is actually being created, why they're secure, and so on, again, you can look for things like Cha-Cha or Salsa. The names are also interesting. These are some well-known secure and stream cipher algorithms. All right. Any questions here?
How do we distribute the nonce? Because before we needed different seeds. The problem was that we couldn't pre-agree on a list of seeds. So if now we need a different nonce, how do we ensure that both parties have the same nonce?
So we send the nonce in the clear. In other words, we don't encrypt the nonce itself. We just send the nonce. The nonce can be publicly shared, and that's the beauty of these stream ciphers. So when we're sending the, as I showed here, when we're sending the information to the other side, we send the ciphertext and we send the nonce with it. So we basically send two things each time we're sending something. Another way of doing this is actually both of them kind of agreeing on the same random number generator, and they initialize it with the same number, and then after that, the nonce will be generated by that random number generator. So that's another way of doing it, but you can just send the nonce in the clear. So nonce basically doesn't add you an additional problem of the key, because if nonce also has to be kept secure, then there was no difference between the key and the nonce. But that's the trick that people use. Okay, so that's it with the stream ciphers. Stream ciphers are also used as the kind of basic block for some other things that we're going to discuss later. But for the encryption, you can use a combination of stream ciphers with your one-time pad and have a fairly secure system with semantic security, and that's really what we want, all right? But we don't use it. What we use instead is what's called a block cipher. So basically, the idea here is that instead of encrypting things bit by bit, basically in terms of stream, we basically divide the message into the block and encrypt the whole block all at once. So we just take the block, encrypt it, take another block, encrypt it, and so on. And the amount of time it takes to kind of like encrypt a block is almost the same as encrypting a bit in some sense. And that's why this is much, much more faster because, for example, the blocks could be 64 bits. And in other words, we kind of like make the algorithm 64 times fast, all right? So this is basically what's called a block cipher, and that's what this AES is about. So AES is not a stream cipher algorithm, it's actually a block cipher algorithm. And in the next few slides, I'm going to discuss what is a block cipher.
So even if I use a stream cipher, like let's say I actually 64-bit or something else, don't I still have to do some function on the block? So why would you have to?
Generating those bits for the stream cipher takes much more time than the block cipher. Once I actually describe what is a block cipher, you will see what's the difference. But I mean, very intuitively, stream cipher is basically, it's a streams of bits, right? And streams of keys that is also bits, and then XORing this together. Block cipher is basically saying that, okay, some number of bits together will be a block, and one block going to be encrypted all at once, basically the same time as one bit.
So like for each bit in the key, you can extract the whole block?
Kind of, yeah. Let me explain it, and you'll get a much better idea of what's going on. All right, so in order to understand what is a block cipher, we need to kind of, again, give you a little bit of background on that. And the good news is that it's not as complicated as the first part. So for block ciphers, we need this interesting, primitive called pseudo-random permutation, or PRP. Remember, in the past, we had PRG, or pseudo-random generators. But here we have pseudo-random permutation, or PRP. So what is a PRP? PRP is basically a function. It's a one-to-one function that maps a domain of X to its own. So basically, it's just a permutation, right? So, so for example, let's say we have 4 bits value. What this PRP does is, this is like a black box. This is the PRP. It just randomly maps this into another 4-bit value, and it's obviously in the same domain. So it's just a permutation. So A goes to C, C goes to D, D goes to F, things like that, right? The important things about the PRP is that PRP should be indistinguishable from a random permutation. So again, what is a random permutation and how do we do indistinguishable? Again, depends on how do we do a statistical test. But to give you some very general overview, the idea here is if we see some pair of M1s and C1s, they're basically the original value and the permutation of that value, and see a finite list of this, and we see just a random sequence of values, we should not be able to tell the difference between this sequence and the random distribution. All right, so that's the whole point of the permutation. And we usually do this, if you pay attention, I'm keep using the term finite. Of course, if we see infinite number of this, we can eventually find and figure out the difference. But we usually do only limited number of queries, basically. We usually call it K queries. So Q amount of queries in order to distinguish these two from each other. What these numbers should be and so on, there are proof for it, which we're going to skip. But for now, just know that there's this notion of PRP, which what we really want to do is being able to commute something from its own domain to its own. So basically, let's imagine 128 bits values. We get 128 values. We just quickly commute it to the same, to map it to the same same domain with different values. Clear? Any questions? So the idea of block ciphers is very simple. If we can build a PRP that is secure, what we're going to do is we're going to take a block of that size of the inputs of the PRP. We're just going to permute it to another block, and then move forward with the next and next. And if the size of this X is large enough, which usually is, so for example, it's 256 or so on, we have 2 to the power of 256, and I think another 2 to the power of that, because there's a number of permutations that we can, or sorry, I think factorial, right? So we have this many possible permutations for different inputs and different outputs, and this is a huge number, right? So the fact that the attacker cannot really brute force this. So we basically permute this into another element in the same domain. And since this domain is huge, the attacker cannot just simply brute force it. And as I said, the PRP should look random. So the attacker cannot tell the difference between this and a random permutation. Because the inputs, so we have, let's say, 256 bits, all right? So the number of inputs is 2 to the power of 256. And then we are talking about the permutation of this. So we can have different permutations. So the first is 256 and 256 minus 1, and so on and so forth. So think about, like, if you have 8 elements, what was the possible number of permutation for this? It would have been 8 factorial, right? So we have 2 to the power of 256 elements, and we want to see the possible number of permutation for this. So that would be 200 to the power of 256 factorial. And this is actually more than the number of atoms in the world. This is this huge number. So it's a very, very crazy number. All right. So, and one final thing to tell you is that there are proofs that this is actually semantically secure, as long as this permutation looks random. All right. So if you can actually do it in a random fashion, this will be semantically secure. There's a proof for that. And there's another major thing that we're going to talk about in the next few slides next time, is if you have multiple blocks, there is a way of permuting each one by one. So you cannot just simply take one and permute it and go to the next one. There should be some relevant relationship between these. And if you don't follow that relationship, your system won't be secure. We're going to talk about it in the next lecture.